So thank you for coming to this talk. So today I will talk about the hierarchically gated deep networks for semantic segmentation. So it's well known the visual recognition task can be characterized into three different categories. So from the classification to detection to the semantic segmentation. So this talk we will focus on semantic segmentation. So semantic segmentation can be formulated as assigning a single label to classify each pixels in an image. So the convolutional neural network architectures has been adapted to finish this kind of task. So image can be feed forward into a fully convolutional network. So it will generate a multiple resolution of labeling result, and the labeling outmap will be fused across the different resolutions to generate the final annotation result for the pixels. So the problems here is we want to see whether blindly fusing multiple layers of convolutional neural network prediction result is optimal or not. So clearly, we are facing a dilemma actually. So on one hand, if we accept the larger scale output from the convolutional prediction result, then it may involve some relevant context, and this may increase the risk to mislabel a target pixel. On the other hand, if we adopt small scales, then we actually may over-segment the regions into small disconnected components with inconsistent labeling result. So our work wants to address this multi-scale dilemma. So we can go back to the earlier stages. So like the shifter features, so the scale invariant feature descriptors. For the shifter features, it actually use a customized scale to extract the features for each target pixels. So our idea is the problem with the shifter feature is a handcrafted feature. So we want to combine the idea of customizing the special context for each individual pixel with the idea to learn the representations in an end-to-end manner. So for this purpose, we propose the hierarchically gated deep networks. So this network has two-dimensional grid of memory cells in each layer. And for each cell, it has the states which memorize the patterns for the target pixel we want to label. Then between two memory gates, two memory cells, we define the gates which control which patterns should be allowed to be merged at the higher layer to form the special context for the target pixel. So here we use the function G, which defines the gate function. So this is a function of a pair of connected memory cells in two layers. So it measures the relevance of states for these two memory cells and whether the state from a lower layer can be merged to the higher layer. On the other hand, we know we do not apply the gating to the memory cells at the same location because we know the pixels are trivially relevant to their own cells. So there is no gate between the cells belonging to the same location. Then eventually we will use linear combination of the memory cells from the lower layers to form the state for the target memory cell at the higher layer. So in some sense, if we view the gating function as the kernels, then our mechanism to form the memory state can be considered as a kind of spatially variant convolution. So the conventional convolutional neural network adopt the spatially invariant kernels. But here we define the spatially variant kernels. These kernels will be customized to each location. Then we use this scheme to form the customized special context for each memory cell. And this is running examples for our algorithm. So suppose we want to annotate the highlighted pixels at the input imaging. Then at the first layer, we will merge the relevant cells from its neighborhood. And then at the higher layer, we will merge the relevant features from the newly added cells to form a larger spatial context. Then gradually, we may be able to end up with a super spatial context to annotate the touched pixels at the input images. So this is we perform the experiment on two datasets. The first is the Steve flow dataset, and we also evaluate on the Stanford background dataset. And we adopt two evaluation metrics: the pixel-wise accuracy and the average label accuracy. And the second metric is more challenging because the different labels are usually much imbalanced in these two datasets. So this is the architecture we use. So we have 5 layers of memory cells, and we have varying sizes of neighborhood across the different layers, and the output nodes will be set according to the number of the output labels for each dataset. Then this is the experimental result on the Stanford background dataset. So we compared with the same type architectures as well as the 2D LSTM algorithm, and our proposed architecture outperforms this compared result. We note that all the models we use to compare are not pre-trained on the external dataset like the ImageNet. And this is a result on the Sift flow dataset. So again, we compare with the same type algorithm as well as the LSTM type algorithms. And we can see that we also perform the other method when all the compared models are not pre-trained. So this is some output labeling result. So these are some good examples, and we also have some bad examples here. So interesting finding for our work is we find even if some pixels are wrong labeled, but usually the images can be correctly segmented into different regions, but with wrong labels. So this problem can be somehow addressed by involving the external dataset. So we can pre-train our architecture on the ImageNet, and then we compare the pre-trained result without, against the model without the pre-trained. So we can see that our method can be significantly improved by involving the by pre-training the models on the external dataset. And in this case, the model can outperform the state-of-the-art fully convolutional network. So some future work. So first, we want to test the proposed architectures on the other tasks like the image classification task as well as the object detection task. So because we believe our representations considers a super scale of spatial context, so it can give us more accurate or better representations for each pixel, and thus will improve the result. Also, we will consider to generalize the architecture from 2D to 3D or even 4D. Then we will be able to test the proposed architecture for the imaging segmentation task as well as the 4D medical imaging dataset.